Hello, I'm Sean McAvaney at the IR Lab at Georgetown University, and today I'll be telling you about work done with Armand Cohen at the Allen Institute of Artificial Intelligence, Nasli Goharian at the IR Lab, and Ross Felice at MedStar Hospitals. And today we'll be talking about ranking significant discrepancies in clinical reports. So for those of you who are short on time, our main takeaways were that we can reframe the task of classifying radiology report revisions based on the degree of discrepancy as a ranking problem, and this has advantages for residents who are trying to learn from their previous mistakes. We find that in the task of ranking, term importance and similarity are effective signals. And finally, that the text representation matters a lot, both in terms of contextualization and using proper training in the medical domain. Radiology reports, in addition to the radiological images that are taken, contain written notes that cover background information, findings, and an overall impression. To ensure the quality of these notes, they go through a variety of revisions. In these particular cases, we see reports that were written by a medical resident and then edited by an attending radiologist. These edits can be purely stylistic, or they can contain substance. So the top one up here, it contains significant edits because it suggests that something was significantly different in the observation. Whereas the second example, there's simply stylistic changes. Since residents can sometimes write over 100 of these reports in a given week, it can be difficult for them to look back and find all their mistakes from all the reports that they've written. In this work, we reformulate the problem as a ranking problem. So instead of classifying these pairs of revisions, we try to rank them in a list. And this setting is actually pretty beneficial to residents who want to find the most important reports to review and learn from. So one challenge is that sometimes apparently large changes can be purely stylistic. In this particular example, we see a bunch of additions, a bunch of deletions, but it could just be purely stylistic, non-significant edits. Whereas here, you might have changes that seem apparently minor, but it turns out they have a big impact. So let's say this green addition right there is the word not. That can clearly have a very big impact on the overall impression of this report. To do this ranking, we model the importance and similarity of the terms in context. So specifically, we model how much a word would impact the meaning of the report if it were added or removed, given the particular context. So words perhaps like not or dislocation could change the meaning of a report significantly. We also measure similarity, so looking at what the most similar word or phrase is in the other version of the text. So maybe it might not be a very big deal if the word small is replaced with mild because it conveys a similar meaning. We use these two ideas to train a model to learn these values from a particular report based on training data that we collect. How do we go from importance and similarity to a degree of discrepancy? We combine these scores over each term into addition, deletion, and overlap scores, and then combine these scores using a multi-layer perceptron to produce a final ranking score. I'll show an example of the addition score. So the addition score is a function of the preliminary report and the final report. We take a sum over each term in the final report, multiplying the matching score in the preliminary report and the importance score in the final report. So an item that's very important in the final that didn't appear in the preliminary indicates a significant departure from the original meaning. And finally, we normalize this to an exact match over all the importance scores. So if we have a very similar text in the final report, it will result in a high similarity score overall. We define these importance and similarity scores over unigrams, so token representations from Seibert over n-grams, so a sliding window over these windows, and ontological matches from RADLEX. RADLEX is a radiology ontology. For training and evaluation, we use data collected and annotated from MedStar. We asked attending radiologists who were making these edits to rate the degree of discrepancy on a 4-point scale, ranging from non-significant to an obvious mistake. This resulted in a data set of 3,368 reports, which we split into 122 sets based on resident week. So the idea is that a resident could look at a report from this at the end of a week and see the most significant discrepancies. We use a 60-20-20 split by resident week for training, development, and testing. We tried out a bunch of different baseline methods, so including the vector space model, using BERT and SciBERT as a classifier, using BiPacker, and using SimReg, which is a feature-based approach that identifies reports with high degrees of discrepancy. We found that our approach outperformed all of these other approaches, so by a pretty significant margin. So we see here using NDCG at 1 and NDCG at 5, simulating a resident who is looking at the top reports. To understand what parts of our model are important, we perform an ablation study where we replace SciBERT with just regular BERT, and we find that that reduces performance, as well as using static word embeddings, both in domain and in the general domain. We also find that the full model without term importance and without ontology similarity also reduce effectiveness, and that the model removing the addition and deletion scores and the overlap scores also reduces performance. So all of these components are necessary. So in summary, we found that we can reframe the task of finding significant discrepancies as a ranking problem, that term and similarity scores can be effective signals for ranking, and that the text representation matters a lot through our ablation studies. Thanks, and if you have any questions, feel free to contact me.